Okay, thanks.
It's just great to be here again today with Delbert Larson, who is a polymath. He's a physicist. He's also a martial artist with, I think, a brown belt. Is that right? And
Yeah, that's correct. Yeah.
and also he's been working on not only a new theory of the quantum luminiferous ether and electrodynamics, but also ecofusion, which is a new approach to a cleaner and safer power source. So, Dr. Larson is here again today to kind of give us an update on how things are going in terms of his work. But before we get started on that, I wanted to ask just a couple of questions about your creative process, if that's okay.
Yeah, please go ahead. Yeah.
Okay. So, what does the day look like for somebody who's working on really big theories like this? What's a typical workday for you?
Well, of course, you wake up in the morning and then and then you grab the computer that's sitting beside you and start to poke through things. And a lot of times overnight, you'll have some ideas. Sometimes even overnight, you might have one that you wake up and you jot down. Those typically aren't particularly successful. I would say probably 80% of the time it's gibberish, but every once in a while, one of them actually is correct. And so then you piece together working on that until you get stuck. In my case, the day that process then ends when I hit my day job, and then I go there. But it's a fairly long commute, so certainly when I was working on the Ether, the radio would be off for the entire time, there and back, and I would just focus on one particular piece at a time. I can certainly remember thinking in my head of spherical surfaces that expand and how that ends up changing things within the Ether until eventually a whole series of things like that led to the equations that came out. You, of course, can't do the equations when you're driving in a car or when you're sleeping, but when you get in front of a computer screen, then you can try to work everything out in equations. And the biggest thing about, I would say, and you may have input on this on your own. In fact, I'd be interested to see if it's the same thing. Is you make a lot of mistakes, at least with the physics theory, and you find out about them by doing the derivation and then getting to the end and finding out something's missing or something's not matching the data, and then you have to start again. So you have to start all over. Normally, it's not a complete start over because certainly the train of thought was pretty good to begin with, but you need to change something here or there, and that tends to be the process. And it can take a short time. Some papers go pretty quickly. It can take many years, and some take a long time. So that's kind of the process, I think.
Well, it's interesting you brought that up about ideas coming to you at night sometimes, and maybe not with 100% success rate, but I was just reading an article about how overthinking something and getting too focused can actually hinder your ability to think something through, and that you need to have time where you're just off, where you have just space to just allow your mind. They were using Nikola Tesla as an example, where he used to just sit and watch the electricity arcing for hours on end, and then the ideas would come to him when he was in that kind of liminal space. And also when you're talking about the ideas coming to you at night, I do remember oftentimes when I would be working on a painting and I had a particularly intractable problem. If I went to sleep thinking about that problem, quite often in the night time, the idea would arrive to me as to how to approach it. And as you say, it wasn't always 100% good, but I often did get some very creative ideas that way. And I think it's because you're just letting your mind kind of rest and get into this backspace sort of. So yeah, that's very interesting. So when you're actually working on the theory, would you say that it's more of like a creative flow, or that more of it is spent on the mathematical precision?
It's predominantly the math as far as the time goes, because on most of these efforts, the math is fairly extensive. It can run into tens to hundreds of pages. And so to try to keep everything sorted out, is difficult. I was somewhat hoping that AI would help out in that regard, but so far at least, it's completely and utterly useless with
Hmm.
regard to a lengthy paper. So that takes a long time. And then when you do work it all the way through, and then that's where you find your problems, then you need the creative portion to come in. And I've often found that when I thought I had a good idea, and I was, pretty certain of it, that what would happen would be that, and it didn't work. What would happen to solve that problem was I was missing something new that I had to add to it. And that, of course, is always a difficult thing to try to come up with because you don't really know what it is you're missing, but it's pretty clear you are missing. That's where the creative part comes in. And then as a shortcut for me, I tend to now always try to have a computer program that I write along with the papers I write so that I can input the variables and then I can input the equations and it does the algebra, not the algebra, it does the computational portion of the work. If it's a real design, such as the fusion design was, or more recently, I've been working on electron cooling for a muon collider, and that falls into that area as well. That you need to know what the numbers are. You need to know exactly how much current you're getting through. You need to know how much scattering is occurring, and you need to know what the end result is as far as what you're trying to obtain. And in those efforts, a computer program can help you a lot. When you're doing the algebra, I haven't really taken the time to try to get that into a computer program because usually what I do is I put in all of the intermediate steps in the paper itself so I can kind of check it fairly quickly. And usually that part converges. That's usually not where the problem lies. The problem normally lies with the hypotheses that you start with. They may not end up giving you everything, covering everything that you need to cover with any given body of work.
Well, so this morning I was listening to a conversation. I've listened many times to this conversation, but this morning it was particularly creative work for me because out of like 15 minutes of this conversation, I wrote like 10 pages of thoughts. And it was a conversation between Jordan Peterson, who's a psychologist, and John Vervaeke, who's a cognitive scientist. And they were talking about the map and the reality. And that the general idea of the way I was thinking about it is that when we live our lives every day, part of what we have to do is match up to reality because any of the places where we don't match reality, catastrophe ensues, right?
It can.
Yeah. I mean, if you step off the curb and there's a car in front of you that is coming at the same time that you step off the curb, then there's a catastrophe there. Or if you step off a cliff because you think that you're impervious to gravity, let's say. Um, those are big examples, but there are a lot of small examples as well. So every day you're trying to match up to reality, and there are times when small errors occur. But very oftentimes, those errors, the way Peterson described it, is the nose of reality poking its way through the map. So the error itself is what kind of points you towards a better way or a better idea, or at least motivates you to keep moving towards something that is going to get you more closely aligned. And I certainly find this when I'm working on a painting. As you said, sometimes you have errors occur in your work. When I'm working on a painting, sometimes I will make an error or something doesn't work the way I want it to work. And of course, the temptation is to just give up because now I have this mess. But oftentimes, the error itself changes the context in such a way that it gives me a new idea for another direction to move. And I wonder if that's kind of what happens for you when you have errors. If the error itself is a pointer towards a new idea.
Yeah, I guess in my case, in physics, the error generally is in your own work, not, as you say, it's not in reality. So if reality doesn't have the error,
Yeah, yeah.
yeah. And so if we've got situations arising that to me, a big one is if it doesn't make sense at all, that should be that a rather huge nose poking through the map, and we should address such things. And in my case, there were several things. I was trying to, with the ether model, I was trying to make sure that gravity, electromagnetism, and their subsets, all of the equations that are known could be derived from a single hypothesis set. So as you start to, the very first thing I did was many years ago, back when I was at the Super Collider. It was over 30 years ago. I worked out a paper to derive Maxwell's equations. Well, okay, that gets you so far, but it was pretty clear even then that if the ether was real, and if this derivation was correct, that meant then that you should be able to derive the force equation. It's called the Lorentz force that exists on particles from the fields. So that was a second thing. And at that time, when I looked at trying to do it, it just failed. So that's the so I guess that's an error on the map that I'm making. It's not an error on reality because the Lorentz force equation is a piece of reality, and it forced me then to rethink things. I set it aside to do the fusion work for probably a decade or so. And then when I returned this last time, I found the things I needed to do to make it work, and it had to do with the electromagnetic flow law in that case. My daughter used to hear about it driving to school. She was in high school at that time. She got a little tired, I think, of hearing about the flow law because it was driving me absolutely insane. Because I would run through all the equations and then I would end up with a minus sign at the end. They're, oh, I'll fix it. So I'd flip something. And when I flipped it, I got I got the plus sign over there, but then I started out, so it was always in contradiction. And that's the sort of thing that was my error, and it needed to be corrected. And there were several of those as the project unfolded. And those are the sorts of things that when you're developing physical theory, certainly we need to address those errors. And I'm critical of the status quo and the way things are handled now because there are obvious errors that uh, originally the authors of, for instance, quantum electrodynamics, QED, uh, Feynman called it a dopey process, what they were doing. They took diverging integrals that went to infinity and just arbitrarily assigned them to a constant that made things work. And it's like, that should be one of those noses poking through your map. But what has happened in the succeeding decades is it got normalized to some sort of an acceptance, which I still find baffling. But in any event, that's a sort of a side issue. But I believe that you should always be on the lookout for such errors, and that is how science will advance. And because if we just want to keep patching up what we have, you can always do that, especially if you've got a mathematical theory and not a physical one, because you can always add more mathematical terms and you can cover up your mistakes. By the way, it's kind of how AI works. It's a giant fitting algorithm that has so many things to fit that you can get a pretty darn close map to things, but that doesn't mean you really have reality at the end of the day.
Well, one of the things I noticed that AI is kind of overfitting is its attempted relationship with the person who's doing the prompts. It will always say to me, "Oh, that's a fascinating question," and then it will, sort of start extrapolating on this question and trying to find a way to represent the information to me in a way that it thinks I want to hear it, which is completely useless. I need an objective partner, So,
Yeah.
yeah.
Yes, yes. And, and
So,
and and the
so
other thing it's doing is there are thousands of people out there with physical theories. And if you've got one and you go into the AI system, and it's going to tell you how great your theory is,
yeah.
and you can coach it along, and then you believe you've got validation, and it's just not true. So it's creating a bit of a problem that way because a lot of people work alone, and a lot of times they don't even submit them to review journals to get a second opinion, and then you're stuck in an you already were in somewhat of an isolated arena where you had a, I guess delusional is almost the right word, and then AI is going to going to amplify that rather than
Mhm.
offer you constructive criticism, which we all need.
Yeah, I think that's really one of the biggest dangers, but I prefer not to live in fear.
Yeah,
Um, so one of the big questions that I have though is when you have something like this that you've been working on now for more than 30 years, this big idea, what keeps you motivated?
I it drove me crazy to not know how the world around me works. And and that was really the motivating thing is I wanted it to make sense. And I'm hardly alone. A lot of physicists that go into the field have tried to come up with understandings of quantum mechanics. That's a big one because the way it's taught now is that's this deep mystery that no one understands. And I honestly I don't I mean I think I have an understanding for it now, but it required that you give up relativity. So it was kind of a difficult uh, road to get or it was a difficult roadblock to get by for most physicists. But it has driven a lot of people. I mean, there's jokes told about it that somebody gave up his career because they were going to understand quantum mechanics. And because when you don't know something at a very fundamental like level like that, it just I just had a very unsettling feeling. I mean, it's somewhat akin to you're walking down the road and you don't know if your foot's going to actually land on solid ground the next time you take a step. That's kind of the mental state you're in when you try to understand quantum mechanics the way it's presently portrayed. And it gets you in kind of a tough spot mentally. So the goal was to, I mean, at some point, if you're a coping human being, you just say, well, okay, clearly it works. I remember sending an email out to the team about like the group I work with on the accelerator side about some ideas I had for quantum mechanics of material bodies, and one of them wrote back and said, "Well, the electron knows what to do," and that was good because you can rest you can rest your head on that one, right? You don't necessarily need to understand everything to know that your foot is going to land on solid ground as you walk down the road. But it still was very unsettling, and that was really the driving motivation then, and for that matter, still, because there's still unanswered questions that until it's until everything makes sense, you want to keep going on it. I don't have to get all the minutia down, like specific instances of what's going on, but things were very unsettling at the most basic levels. The biggest one being that relativity and quantum mechanics didn't work well together. Something had to go, and you go down that rabbit hole, it's pretty deep. Actually, the quantum mechanics one wasn't very deep once you go down and try to set relativity aside, but that one there's a lot there and a lot of work, and there's a lot to try to challenge and come up with something that can agree with all the experimental tests. So I hope that covers
Yeah,
the
yeah. Well,
quest.
so if you have to set relativity aside, then you also have to find some reason, some understanding of why quantum mechanics works so well in all the arenas where those calculations are being used today in computer science and communications and all these kinds of things. So how did you manage to work through that?
Well, the you can set relativity. Okay, so there's a couple levels of this. The first thing is that what works extremely well to build everything that we do technically are the basic equations that we use to make things. And you're spot on that quantum mechanics does play a role in several arenas. Its foundational work was done by either Heisenberg through a matrix mechanics approach or Schrodinger for a wave mechanics approach. And they each developed some equations. And Schrodinger's equation can be derived fairly nicely from assuming an underlying physical model. And then you can go ahead and develop that equation. Einstein's relativity was based on his famous postulates. His special theory of relativity was based on his postulates of a constant speed of light and the proclamation that every observer would see the same laws of physics independent of their constant motion with respect to one another. But prior to Einstein, there was a gentleman, and we covered this last time on about a year ago. There was a gentleman, Hendrik Lorentz, who worked for years along with others. Fitzgerald was one, and Larmor was another, and Poincaré, and several names that predated Einstein that came up with a theory that when objects went through the ether, because there was an ether that was viewed at that time to exist, that those objects as they went through it would shrink in size as they go through the ether, and any clock going through the ether would slow down. So there was a ready theory there that had this length contraction and time dilation. And Einstein's special relativity derived the exact same equations as special relativity has. There was no difference whatsoever. So it was very easy to step away from relativity at that point. So at that point, we would then have the special theory of bodies moving through the ether that map all the equations that we need, and we would have for those cases, and we would also have the equations of quantum mechanics. And the one thing that we gain is in the ether theory, time was absolute. That is the critical step of being able to understand quantum mechanics. Where you run into trouble is if time itself is relative to your motion, because at that point in time, you've arrived at the point where distant events cannot affect one another in a way faster than the speed of light. It's baked into the cake of special relativity. But as long as the equations for both are identical, you just set special relativity aside, say we're going back to the ether and everything's good to go. We can still build everything with a major exception. And the major exception would be the GPS systems that rely on gravitational time dilation. And what that means is now you have to also come up with a theory that gives you the exact same equations that general relativity gives you. And general relativity is a vastly more complex mathematical structure to try to understand than is the simple Lorentz transformation equation that backs special relativity. But once you've done that, once you have come up with a ethereal theory that provides the same equations as general relativity does for massive objects, then you have achieved the goal that all the equations still work. That we rely on to build everything we build. And it also opens up new areas of possible research to go forward with. One of those presently, certainly in my work, is the analysis of dark matter, because it's very well predicted as to where the dark matter should be, and that is a prediction that's capable of being tested through observations. And really, in some sense, there's no dark matter, because really what it is it's, well, you could call it dark matter, but it's the mass that's associated with the fields of the ether when the ether is disturbed by massive bodies. So you add that in, you get all of the equations of general relativity, plus you get a dark matter prediction equation, and that's where things stand now.
So what would be the likelihood of that being observationally proven or verified?
It could be tested the key step is to be heard and to have those who are who have access to the telescopes to do the relevant calculations. They would need to just base it on the theory that I've written and see if the stellar trajectories match match the prediction of the dark matter existing where my theory says it should exist. The most simple example. Sorry,
so you need an astrophysicist who has access to the telescopes, who understands um, the current theories of dark matter and would be able to kind of integrate your theory in their calculations. Is that?
it's close. They wouldn't actually need to understand the present theory necessarily. And not only that, there are a couple of examples that are well known that I've already matched things up with. Most spiral galaxies have enormous objects at their center, and they're also surrounded by a lot of stars near that very large object. So most spiral galaxies have a very massive core at their center. And it's at the edges of those galaxies that it's clear there must be some dark matter, some matter that we don't see that's causing the velocities of those distant stars to be what they are. And that those examples are already treated in the paper I have. There's also something that's fairly famous that I just opined on here, I think a couple days ago, maybe it was yesterday, which is the bullet cluster. There were two colliding galactic clusters that passed through each other. And these galaxy clusters had an enormous amount of gas with each one of them. The gas interacted with the other galaxy cluster's gas and ended up leaving the gas in the middle. But the stars, since they were so much more massive and they didn't have the same DEDX forces on them, sailed right through each other. And the thing that happened in that case then is you've got a very large amount of gas in the middle. And from what I've seen, and I'm not an expert, and this is where it would be helpful to have somebody really scrub the numbers and say, well, okay, mix it or not, is the gas has more mass in it than does the galaxies that are on each side of it now. And yet the dark matter appears to reside with the galaxies. And my theory would expect that, because what happens is that the dark matter results from the ether being displaced by the massive object. So if you've got this big heavy thing in the middle of the galaxy, it's going to have a fairly large gravitational field near its center that drops off as 1/r² as it goes to the edge of the galaxy. And that means that you've got this ethereal displacement that also drops off as it goes to the outer edge. And when you integrate the amount of energy that would be within any given sphere going outward from that center, you end up with a 1/r force that begins to dominate toward the end. And that's why you get what you see within a galaxy. But if you have two galaxies that are neighboring one another, halfway, and they're the same mass, say, halfway between, then you won't get any disturbance at all. So the amount of displacement will be zero, and you won't get any energy there from the displacement because there's no displacement, and the dark matter would go to zero. And also, if you've got a big diffuse mass, for instance, a body of gas that's sitting in the bullet cluster, then the gravitational field is not all centered in the center anymore. It grows linear. If you've got a fairly constant density of gas, and I don't know the specifics, but you no longer have that very heavy central object, you're not going to get the same footprint for where the displacements are, and you would expect the the dark matter to be vastly less. I have calculated those situations for what are called ultra diffuse galaxies, and it matches the data there too. And where the help would come from is if someone with a lot of astrophysical data would take this model and then try to map out uh, where the dark matter should be observed, and then also match it with the observations of where it is in regions outside of the ones I've already considered, and do it in more detail to try to determine how good the fit is,
Mhm.
because it should be that there's no dark matter particles outside of this. There could be those too, though, of course. You have that possibility. That would be unfortunate because it'd be easier to prove it if it's not there. And one of the things that is a fact is there are neutron stars all over the place, and they're going to be dark and they're going to look like dark matter. So there's going to be some noise in this, but that the prediction can be tested against observations. And from what I understand, there have been other gravitational theories that have fallen, and uh, by these sorts of observations comparing against them, and I would welcome a serious study to see if the model I've come up with it does fit the observational data.
Well, I know that the JWST data has caused a lot of changes in the way people think about neutron stars and black hole densities and all of those kinds of things based on observations that the JWST has been doing. I might have gotten the particulars wrong there, but I know that there have been some questions that have arisen because of the new observations of the JWST. So I guess basically my question is, has any of that illuminated any part of your theory, illuminated it or eliminated it, either one?
Well, that will be important to look into. I haven't uh, taken a deep dive into that at the moment yet, so I will take a note and I'll
Well,
see what's online.
I can also try to round up some of the things that I saw that led me to have that thought in my head just now. I know that they've talked a lot about neutron stars and white dwarfs and black holes. So a
Yeah,
lot
that
of
will all
things that
be
they've
relevant.
just the JW one of the biggest discoveries that the JWST has made is that there are intact, fully formed galaxies much closer to the beginning of the Big Bang than what they ever expected to find, because it
Okay.
appears as though there's not enough time for a galaxy to have formed, and yet there they are. So,
Yeah, one of the problems I have with it is I need to know more, and it would be great to have a discussion with an expert, is how reliable the distance ladders are once you get out that far. Because from what I have seen, present standard theory is that white dwarfs the supernova, there are certain supernovas that occur from white dwarfs when they accrete matter from a partner. And once they reach a certain mass, they explode. And the theory is that those supernovas will always explode with pretty much a constant luminosity because it's going to occur at a very specific mass that Chandrasekhar worked out 80 years ago or something like that. And my view is that I don't trust that number. I don't trust the process because from what I've seen, the theory is that the entire white dwarf star is treated as a single quantum state. So you've got something that is of enormous size, and yet you are saying that it's a single quantum state. And I put together a different modeling in my larger Aether paper, where instead of treating it as an entire body, I treat it as a being made up of cells, each of a certain size, and that the cell size is determined by when the quantum mechanics tells you that an interaction, coupled with the thermal motion, it'll tell you when an interaction will occur, and that kind of gives you a bounding box for the electrons within it. And then I integrated those cells outward, and I did things that way. And instead of it hitting a certain density when this, and then the whole thing just buckles because it can't support the incoming gravity with the degenerate electron pressure. Instead of that being the case for it to blow up, instead, I believe that at the very core, you may reach a pressure where you start to get neutron formation and it begins to collapse on itself. And as it does so, it's a chain reaction. And then it will blow up in the same mechanism that is presently theorized because you've got all this fusion fuel that gives a very big explosion. But the thing that triggers it is different. And if the latter trigger is correct, then you're going to have issues associated with the specific conditions of what's going on in that core. How hot is it? If it's a lot hotter or colder, it's going to blow at a different amount. So that then triggers you back to saying, well, if these things aren't constant, then where are we on these very distant events? And I don't know where the theory or where people are now with the thinking on each step of that distance ladder because I'm not really a cosmologist. I'm back at the basics of
Mhm.
all of it. But it's that sort of thing. I mean, I'm very interested still in seeing what the data says, and I want to look at it. But whenever anybody says these things about things happening so far away, that there's a I have that the one question about how well the distance ladder is working. And then the second one is, what's to say that at scales of space that large, that things are identical there and all the way from here to there, that they
Mhm.
are here? And there's several really large assumptions involved. In fact, I didn't even start to look at gravity until I guess it was less than 10 years ago, just because of that fact. And that fact, and also the other fact that you can't really do controlled experiments. You can only do observations. You can't like just make a star and then take one away, and like we do in high energy physics. High energy physics, you can actually collide things and you have control over it and very, have your control variables and all those things and make changes and see how your equations react to the changes. When we're looking at astrophysics, you're stuck with what's out there and what's actually happening. However, I was convinced by someone in a chat room once that, the data out there's an awful lot of it. And so maybe you should reconsider your approach. And it was about that time. Yeah, he's probably right. He or she, I'm not sure. Because it was, it's blind online, you don't know. But in any event, at that point, I started looking at it. But so those questions still are there, that we should always remain quite humble and not say, well, we know, especially when you're talking about things on the other side of the galaxy.
Well,
But anyway, that's a
regarding
bit of a rant.
distance, and this may be a completely irrelevant comment because I don't know this stuff at all, but in trying to follow a few of the rabbit trails that I ran into when I was looking at your work again, I was trying to understand the length contraction issue. And one of the things that AI brought up to me was the the thing that happens with muons, that even though they exist for such a very short period of time, somehow they're still able to get to Earth. And that is because this is what AI said to me, that the using the Lorentz transformation, you can see that the distance has contracted so immensely that the muon is able to get here with and still be existing when it gets to Earth. Now, does that make any sense to you at all, or is the AI just confabulating something?
Well, that's the standard view, and I think it's pretty well. The one thing that I believe is proven without any doubt is time dilation. And from our standpoint, watching those muons coming in, they're coming at a very, very high speed. So any clock that would be associated with them coming in would be running way slower, and that's why they would arrive at the Earth. When AI said that the length was shorter that they went through, that's because the Lorentz transformation has been applied so that the analysis is not from those of us here stationary on the Earth, but it's from an observer moving with the muon. And so at that point, the theory goes that the length has shifted so that it has now shrunk. And in the relativistic way of looking at it, that is the correct answer, because in relativity, time and space are famously relative, and that's why it's called relativity. And so the what was a longer length for us has become a shorter length for the muon. What was a and worth and for time, what for us was a certain amount of time, that was actually a much was shorter time for the muon as it's going through. Yeah, because it only lives a shorter time as it sees itself. So, but when you have an ethereal theory, then things are a little different, because Lorentz's approach was that the only observers that had the right measuring apparatus to measure space and time were those at rest with the ether. And in this case, since the muons are coming so fast, we assume that we're the ones that have the better equipment. That's always a dangerous thing to assume too.
Mm-hmm.
But if we make that assumption, then some of this becomes a little bit more dicey, because now you've got more of an absolute characterization of what length and time is. And so then what you would say is that the muon's clock was running slower, and since its decay is also is something that could be treated as a clock, it lives longer as it moves. So it was kind of a longer-winded answer, but that also gives a flavor to the difference between the ethereal theory and the relative one.
Mm-hmm. Wow. Yeah, that's really cool. Well, I've pestered you enough with my questions now. Now, I'm guessing you had something that you wanted to present, some new aspect of the theory, and also kind of an update on your ecofusion work, because that is going to be end up being very important to the world, I think. So.
Oh, okay. Thank you. I guess the update would be I got a quantum paper out since the last time I talked to you that derived a new equation for quantum mechanics that was, they call it relativistically correct, but since I'm not a relativist, it's a little bit awkward. So I guess you could call it Lorentzian correct. And it works when the potential energy is a significant portion of the rest mass of the particle, where Schrodinger's equation tends to break down in that arena. And it also answered a few other questions on quantum mechanics that made quantum mechanics make sense, because there were about three different issues involved there. One was uh, the issue we've already discussed about it being incompatible with relativity, and that's easy enough to handle if you just set relativity aside. But there were a couple of other issues that have been kind of haunting uh, quantum mechanics for a while, and that is that if you look at matter waves in the standard theory, they are moving at a superluminal velocity. Now, nothing's supposed to go faster than the speed of light by relativity, and yet here these waves apparently do. And the answer that was always given was, well, they're not physical, so you don't worry about it. And then the second one was that if you do a two-slit
Did you
experiment,
say matter waves?
yeah, matter waves. That
What
de
isn't
Broglie.
that? Is that like a gravity wave or no?
No, this is okay. So if you can do a two-slit experiment with light, and I think you're familiar with that. You
Mm-hmm.
get the
Very.
pattern on the wall.
Mm-hmm.
You can also do one with electrons. So when you do them with electrons, that shows that the electrons also are entities that have some wave characteristics, and they will interfere at the distant wall as well.
Okay,
In
and so
fact, you
that's called a
can,
matter wave. Yeah, I'm familiar with those experiments as well, but I didn't know
okay,
that was called a matter wave. Okay.
okay, yeah, yeah. So those are matter waves, and the problem is if you look at the theory, you end up with the wave velocity going faster than the speed of light, and the group velocity goes slower because it moves along with the particle. And the problem you have with that is then if you analyze the two-slit experiment from two different frames, and this is the response that I got about, well, the electron knows what to do, was if you can analyze it from a frame such that it shouldn't interfere at all. And it was kind of a very confusing situation. And so that required a bit of a modification to de Broglie's original idea. And then and then so that one ended up hitting de Broglie. And then to get the phase velocity so it wasn't superluminal, I also needed to make a modification to Planck's original empirical observation for light, because that's typically also applied to the matter waves. And in both cases, uh, but in any event, at that point, everything did work out so that all of the paradoxes were resolved. And I don't, but it required three steps. And the main thing that I would like to advertise about that is that both Planck and de Broglie were, I mean, de Broglie proposed it without necessarily having empirical evidence, but Planck's was certainly based on empirical evidence. And then later, de Broglie's was validated by the empirical evidence. And if we now modify those empirically derived formulas, we're still on perfectly sound footing, provided we agree with all observations, because that is what physics is, or at least used to be, was an empirical science. And so it should be perfectly fine. So once you put those two things in, plus you set relativity aside, then my claim is that you can understand quantum mechanics to the level that people presently find not understandable. There's always going to be the next question of why and what's going on underneath. But at least the present things that people trip over, uh, that was handled in the paper, I think. I mean, I believe. And then another aspect to it was that there's this issue of the collapse of the wave function. And the proposal there was that it always collapses whenever momentum is exchanged with it, or even if momentum is required to be transferred in a certain region of its existence, but it isn't in other regions, then it will collapse to the region, either to the region where it is required, then it'll be like a speck on a wall, or it'll collapse to the entire region where no collapse is required. And that gets you an understanding of what's happening in the two-slit experiment that I believe has been largely missing when people try to use concepts like wave particle duality, or say that it's has something to do with information, or any number of ideas. Multiple universes are at play. So, so that was one thing that was done in the last year. And then more recently, I soon have a paper coming out on Ethereons. And I had on my website, we never really went into detail, I don't think, on the Prion model, but my view of reality is quite different from the standard way that people look at things now. The standard model has a series of fields, and it's a quantum field theory with fields for all these different particles and excitations that have been found. And the the idea I've seen expressed, and a lot of times it's kind of difficult to nail it down because it's not really a physical theory. It's a mathematical theory. And when you run all the calculations, it agrees with the experiments. But when you start to ask the questions, it's like, well, is it like, is the electron a particle or a wave? And things like that. It gets a little bit dodgy. But one of the answers that I've seen is that the electron is a instantiation of the Dirac equation for a pre-existing field. It's that kind of thing. Whereas for me, the electron is a blob of matter that vibrates. It's got size and that sort of thing. So you start there, and then you can ask questions about, well, is it made of something else? And and sort of that has been done with regard to things like the proton and the neutron. People presently believe they're made of quarks. And my interest long ago was I saw a pattern that the quarks and the leptons could be made by a smaller number of primitive particles that would make them up. And there was a word for that at that time called preons, and it hasn't really had a lot of work done on that. This was in grad school, so this goes back over 40 years ago that I started on the theory, and that got developed later. Uh, and I published a paper while I was still at the Super Collider, and then again, not too long ago, I published an update because it matches the data very well. That instead of having these quarks and leptons, if you have these preons, they you have a lot fewer particles that can still give you all of the data that's seen in particle accelerators. And it also makes a whole slew of predictions that people could look for. And I would, of course, really welcome such an effort there too. So that was the preons. So that's somewhat dated, but it's background information to what's been done recently, because the Aether model to date handled electromagnetism and it handled gravity, but it didn't handle nuclear forces. And I was fiddling around with it, and I thought I wanted to start working on the uh, how the ether could perhaps generate another force. Presently, in the standard model, there's four forces. There's electromagnetism and gravity, and then there's a strong and a weak force. And long ago, I had identified that the weak force really isn't a force. It's actually a radioactive decay of the quarks, and by they'll emit a preon, similar to how a uranium atom will emit a alpha particle and decay that way. And it all works very nicely to predict everything we see. So I didn't think there's a weak force, but there certainly is a strong force. And so the question was, where in the ether could that manifest? And you mentioned last time I was on that uh, it might be that things are twisting. And then I've seen online also that people say how important spin is. And I just thought, well, okay, maybe what's happening is the ether's when things are spinning inside it, the ether twists. And if it does that and it really doesn't want to twist, then if it finds another one that's going to twist it back, it's going to want that state, and there will be an attraction there. So so then I was looking at the ethereal quantity itself, and it had certain quantum numbers that it has a spin. They had a spin, and they had charge, and so I was thinking, well, maybe somehow they end up building into the preons, and I spent some weeks at it, playing around with it, and I eventually hit the what I think is going on. I was running into a difficulty because the numbers weren't all adding up until I realized that perhaps they're not in what are called S states. In an S state, the two particles won't have any orbital momentum about each other. They'll just have their own intrinsic spin. But when they do orbit each other, you're going to pick up some more angular momentum, and that snapped everything into place. And then what that ended up determining was that the those freed etherions made up the preons. And so if you just go one step deeper than the preons, so you go from, you know, us to molecules to atoms to nuclei and electrons to quarks and leptons. And then if you go one step lower than that, you've got your preons. And if you go one step further, then you're getting these constructs of the etherions. And it turned out that a freed etherion, a single free quantum of the ether, had identical quantum numbers to the B preon, and that the A preon and the C preon were combinations of the ethereal quanta and its partner. So you then have a situation where everything we know is made up of these two particles interacting with each other. they tend to predominantly lie in the background. It's enormous. Uh, I did a quick calculation because we had this talk today, and a rough estimate, and this is really rough, is that the density of the ether then turned out to be approximately 50 million times more than nuclear densities. And that makes an assumption that the background ether is aprions, because aprions are a positive preon orbiting a negative preon. I don't believe that's really what it's going to be, and this number is highly sensitive to what the potential is, but we do at least have a data point, which is the aprion that we can make an estimate of. So the picture that
So then
evolves,
would the C preon be the negative
the
orbiting
C,
a positive?
okay, so the aprion is the negative orbiting the positive. The C preons are a negative orbiting a negative or a positive orbiting a positive. That's how all of the numbers came out.
Okay, so the A preon is the
A negative orbiting a positive.
okay, and C preon is negative to negative or positive to positive.
Correct. The C preon always had a charge of +2. That goes back decades. The A preon was always uncharged, and the B preon always had a single charge. So the B preons, there's a plus and a -1, and those are the plus and minus ether particles. And then the C preon is when two like particles are bound together, and the A preon is when the opposite particles are bound together. And then everything worked. And you can also see that it's one of those situations where I stumbled upon something that was necessary and sufficient, and you didn't have anything left over.
Mm-hmm.
And you don't have anything left over anywhere, because now you've got this huge dense sea. There's been, you get these sci-fi things, right? Oh, are we living inside a black hole? No, we're not living inside a black hole. We're living in a giant ball of ether, and it's exceedingly dense. It's, again, 50 million times denser than neutron stars. But the way all of the fields work out, you don't notice it. And then what we see as particles, what we see as neutrons are free ether particles that are a very small percentage of the density of what the background is. And that builds everything, because these various preons now then build up to make the quarks and the leptons that we see, and it makes everything we see. Now, not quite everything, because the other thing that you have is you do have waves on the ether, and that's light. It's gravity waves, and it's probably neutrinos. And that's where the theory stands now. And where I want to head with it is to pursue the strong force. I've got a lot of notes written, but I got diverted on a couple of things along the way. The muon collider being the biggest one right now, because I had something that went to help that, and the work that I have proposed to the DOE, that addresses a muon collider need, is the identical work that one would need for ecofusion. So if you want to ask some more questions to follow up on the Etherions, we can go there for a bit, or we can move on to ecofusion soon.
Um, I do want to ask you a question about the ether, or at least I want to tell you something.
Okay.
I don't know if it'll be useful to you, but it's one of these ideas that's been haunting me, drawing me, dragging me forward for months. In cognitive science, there's this idea of how reality comes together for each individual is through the process of perception. That in order for us to really see anything, because we're looking out at, I mean, according to the quantum physicists anyway, we're looking out at a sea of particles. And somehow our eyes and our mind and our thought process is able to see where the things are in that sea of particles. And part of the way that we do that is through our process of perception. And perception requires that you have some kind of a frame because the frame limits. If you're looking at infinity, you need something that will limit what you're looking at so that you have some way of seeing what's there. So perception is a kind of a limiting process. And I don't want to go into it too much deeper than that, but let's just take that perception is a kind of a limiting process. Well, I ran into this verse in the Bible. It's a very well-known verse, Genesis 1, chapter 1, verse 9. And in there, it says, after God has said, let there be light, let the waters above the firmament and be the waters below let the firmament divide the waters above and the waters below. And then it says, and then God gathered the waters to reveal the dry land, so that the dry land would be revealed. I thought that's very different than all the other verses where God is saying, let this happen. In this verse, it's saying he gathered the waters so that the dry land would be revealed. So that made me curious. So I looked up the Hebrew for the word gather. And in that verse, the word is kava or chava. I don't exactly know how to pronounce it. But every other place that word appears in the Old Testament, it's translated as hope or anticipation or expectation. And I think that somehow that is the picture of the meaning of perception. That in order to know what we're seeing, we have to have an anticipation. We have to have a hope. There has to be, the cognitive scientists talk about inside every organism, there is a map so that they know what's outside of them. That map has to be built into us. Otherwise, we can't perceive the universe around us. So if that's true, then if Genesis 1:9 is the picture of perception, what it's really showing us is that hope and expectation are at the foundation of the universe. And part of what that is gathering the waters is a picture of bringing together the chaos, holding in the chaos, so that the dry land where humankind will thrive and will grow, the dry land can appear. So it's pulling back the chaos so that the order can appear. And so when you're talking about these A and B and C preons, the way that they're orbiting each other and everything, I almost get this picture of that is a very orderly process that has been revealed by pulling back the curtain kind of on all the chaos that's been happening in these mysteries of quantum mechanics. Anyway, that's my thought for today.
Well, that's a great picture because the chaos is the standard model itself. If you look, I don't know if you've ever looked at the equation itself. It's got over 150 terms. Many of the terms are these strange things that if you find out what they really are, they've got 16 terms themselves. And so there's a huge amount of chaos that's there. And the picture you pointed about, you've got all this chaos and what you want to find, I think, still is the the simplicity that underlies what's happening there. Because your picture was of the water's chaotic because it never stays at one place for long, and you need a point of dry land to make some clarity out of what it is you're trying to do. And that is a goal, certainly, in physics, is to take this huge amount of data that's coming out of these accelerators. And by the way, even though I always disparage the standard model because of its complexity, but if you look at the amount of data that goes into it, it already is a big simplification of the sheer volume of what people are looking at to arrive there. And so we make one step at a time towards the ultimate simplicity that we're looking for. that should underlie everything. So I think that ties in pretty well.
Well, also you mentioned before that the you were talking about the strong force having to do something with perhaps a twisting that's happening in the ether. The thing
Yes,
is twisting inside the ether, and then the ether has this push, this desire to get back, which
yes.
requires the twisting back. Well, that desire to get back, I see that like as an anticipation or a longing for to get, as though, one of Aristotle's causes is the final cause, that there is a picture of what the world, of what reality is, and we're moving towards it. We're not there. We're always moving towards that picture. There's
Oh,
something in all of creation that longs to be drawn into that ultimate picture of reality, and that longing is that anticipation. So when the ether twists one way, it has this longing to get back, because that longing to get back is that longing of moving towards ultimate reality.
yeah, certainly I think that you can phrase it that way because I mean, I tend to look at it as it twists, it ends up in a higher energy state and it wants to get to a lower energy state. But that could be termed as a longing to do that. Yes, yes,
So it's twisting from a higher energy to a lower energy state. So
yeah,
have you
yeah.
looked at all into this whole idea of Carl Friston's free energy principle?
No,
Okay,
but
that's something I think you should look at, because that is really making the rounds, not
Carl who?
only in cognitive science, but also just in, even a lot of physicists are looking at it now. It's called the free energy principle, and Carl Friston, Friston.
Okay,
It has a lot of implications. It's a fairly simple principle, which I'm not going to go into now because I still want to get to your ecofusion, but I do recommend that you look into that. I think you find it very interesting, especially with what you just said.
thank you.
There's a
I'll
fit
take a
there.
look. Yeah.
Okay, so let's look at your safer power that you have come up with, because that's very fascinating to me. And you said you've been in contact with the DOE about this?
Well, no, I'm in contact with, well, I've been in contact with the DOE about this for probably 12 years or more. And I've never been able to successfully get any funding yet. In fact, when I first finished, I went to a local uh, venture capital firm. It was called StarTech, north of where I live. And I made the rounds and met, I would never meet the person with the money. I always met their handlers.
Oh,
And it never got past that. It's like it was kind of neat because anybody that had money had, a lot of them had physicists. They had their own in-house physicists to vet, what they wanted to do. And it never got by them. And some of the times the interviews were quite good, but the experiment was going to cost too much. And it's like $20 million ish. And then I also tell them that I certainly am not guaranteeing it's going to work at the end and to produce power the first day. I do firmly believe that it's the proper way to proceed. So that project was another driving thing for me because when I was young, I was told that we were going to run out of energy in the year 2000, and I thought, oh, this is horrible. So I was studying, and then we hit 2000. I was, oh, things are still fine. What's going on? And then I talked to a friend of mine who had knew somebody who was an oil engineer, and he mentioned that, well, they've been finding a lot more. He said the era of cheap oil is over, but not the era of oil. And of course, even then, people learned to make it to get it even cheaper. So we continue to move along. But that drove me in any event. And so I spent 6 years working on that design. It had the same sort of pitfalls that that we talked about. I'd get to the end and there'd be a problem. I'd get to the end and there'd be a problem. And it just took longer and longer. And I finally got there. And then I went out and I thought it would sell immediately because it's like this is, you believe in your own stuff, right? And it would change the world. The fusions, there's something roughly 10 million times more energy in water than there is in gasoline. And when you're done, you get your gallon of water back. It's it's I mean not the whole gallon, but I mean since the ratio is so large, the fuel is super abundant, and the amount of energy you get out is great. So people have known this for, let's see, I guess 75 years now. And there was an idea called the tokamak that has taken all the money, uh, that does get somewhat close, and the diehards are certain, and I don't even necessarily want to call them diehards, but the believers, put it that way, are sure that we're not too far away, and that may be true. But wasn't when I started, and I don't know that it is now. I mean, we'll find out when this next wave of experiments go through. But in any event, colliding beam fusion had been tried before, and it failed, and there was a known reason why it failed. And first of all, I guess it probably makes sense to give a bit of an introduction. We've got little time. We should have enough time for it. The way that the tokamak works is you pump essentially hydrogen in two different forms. One's deuterium, which is a proton and a neutron, and the other one that's most likely to be used is tritium, which is a proton and two neutrons, and you heat it up. And when you heat it up enough, then it will collide and it will make a helium atom and a neutron and about 17 million electron volts. And then those two particles will go out. And one thing you could do with them is have them hit some container that would then they'd slow down by a DEX process, although the neutron has to be converted to a proton before it would lose energy that way, but that's handled because you can put certain materials in the way to make that more likely. And then that's going to boil your water and turn your turbines, and on you go. But the problem is that you need a lot of it, and you can't have one interaction because that's next to nothing. And so you need a lot of deuterium and tritium. And so you've got to store it somehow. And the way it's stored is there's a big circulating magnetic field, and the particles do circular motion around this thing. And then every once in a while they'll bump each other, and sometimes they'll fuse. But some other times they'll bump off each other and they'll start wandering off to a wall. Some other times they might start oscillating around. If you don't have any electrons in there, they would immediately blow up and hit the walls because of their own self-repulsion from the space charge. So you have to have electrons in there, and that's called, and then you have what's called a plasma. And there's a whole slew of instabilities and whatnot in that device. But it's shown some significant progress, and there's a big effort on it called Aether that's going to spend billions of dollars to try to finally get above the hump. So that's the competition. Uh, the more simpler way to try to do this is to take a beam and accelerate a beam to the exact energy you need that maximizes the chances for this fusion to occur. So you want one beam of deuterons going one way and another beam of tritons going the other way, and smash them together. And that has an enormous advantage right there, because in that plasma I was talking about, it's a thermal distribution. And so the vast majority of them aren't at the right energy to fuse. This way, every single one is. And then what you would want to do is you want to focus it down so your chances of colliding are optimal. And since that's a rather obvious idea, it was tried and it failed miserably, because what happens is that most of the time they're going to miss. And when they miss, they don't just cleanly miss, they get a small kick most of the time. Sometimes they get a large kick and they're gone. The small kicks, unfortunately, when you bring them around again for a second try, those things add up, the random walk problem, and they leave too. And you end up having them leave way too fast for you to get useful fusion power out. So the idea was abandoned, rightly so at that time, because it was proven and shown in the experiments and everything that colliding beam fusion isn't going to work. But we knew what the problem was. It was this accumulation of these small kicks that these particles were getting. And my PhD thesis was on a process called electron cooling. And for electron cooling, what you do is you take an electron beam that's moving at precisely the energy and velocity precisely the velocity that the ion beam is moving at, that you want it to be moving at. And then what happens in that electron beam is, if that ion beam is kind of off angle, it's going to collide against those electrons, which are like perfect. And so it's going to straighten out. So all of those small little kicks that you get as you cross that path are going to be corrected for. Now you have the problem that, okay, that energy that you just absorbed in the electron beam also has to go somewhere. Well, you dump it into a collector can at the end and you collect your beam there. There's going to be inefficiencies. And then you need to also look at the magnets that you're steering this other beam, because you want to keep those deuterium and tritium ions in this colliding system as long as you can. You want to give them as many chances of fusing as possible, because you've invested energy. You put energy into each one to try to make this happen. And if you just threw it away, again, you would lose. You're not going to win. So you have to store every single little piece of energy through this whole system that you possibly can. You can use permanent magnets in the system, so you don't need to have electromagnets draining you of electricity there. The electron beam itself most of its energy can be recovered at the end. You can't recover all of it. You've got some thermal processes that are taking place. And after I did the full analysis of the whole system, because my background was as an accelerator physicist, I finally got a system that, when I included everything, I ended up with a system that, on paper, got 2 times the energy out versus the energy in. That's probably not enough. But at that point, I thought, this is huge, because nothing's come close to that yet. The tokamak systems are not close to that yet at that time. Sometimes you'll see people claim that, oh, it went over, but it might go over for an exceedingly short period of time. I mean, nothing's ever been able to actually work. And my viewpoint on this was that, okay, I've got the base camp, right? We're still going to be climbing the mountain, but I got a base camp. We should build this thing and we should see what's going on, because at every step of the process, you can continually look for ways to lower that input energy to raise the ratio until we reach a point. I think I wouldn't think it would take too long, that now we can get this to be functioning as a system that produces energy for us with an energy out over energy in of approximately 10. And there's a bunch of nuances here, and I've looked at a few things. I think the present design is pretty good. The problem you run into is you're still dealing in this colliding region. You've got to have electrons there. So I've modeled what they would look at, and so there's some modeling involved, and you really need to build it and try to see and then take measurements. And so it becomes a scientific project. And that's why people say, well, okay, the tokamak's going to work in 5 years. We don't need you. Or lately it's, okay, I've seen a lot. Elon's big on solar. That's going to take over the world. And well, maybe, but you're not going to get from here to the next star on solar, because you're going to run out. It's not going to work for us. So, and besides that, there's an argument about the unreliability of solar. It doesn't work at night. You can have a hailstorm come out and take out a lot of the system. I don't know what the long life of it is, as far as how long things last. I'm not a real expert on that field, but I do know also it
Not to
takes a
mention
lot
how
of
many
mining.
birds it kills.
Well, that's more the windmills. It does solar may too.
Oh yeah,
But
because of the reflection. So
oh, okay.
the heat focus going back up is, yeah.
Oh, you may know more about the drawbacks than I do. But and the land use and the
Hmm.
mining, and there's a lot of, it's not there's a place, I think, for fusion. So that's the eco-fusion story. And where it ties into the present effort is that the next big collider for high energy physics is being debated as to what we're going to do next. And one of the candidates is a device called a muon collider. You mentioned earlier that the muons only live a very short time, and that time is 2.2 microseconds. And yet the dream is to accelerate them so quickly that they'll be moving so fast that even the example you gave earlier about how long they live in the atmosphere, they would it's called a gamma factor, how fast they're moving. It gets so large that they can live long enough to make a a collider out of them. The problem that the muon collider faces is not only do they decay quickly, but they also, when you make enough of them to make a collider out of them, they are made at a very high emittance, it's called. And basically, the emittance is the multiplication of an angular spread and the spatial spread of the particles. That tells you how tightly you can focus it. You've got to have a certain minimum value to make that happen. And this same technology I described about the electron overlapping the deuterium and tritium beams can be applied to these muons at a source. Now, it's a monster of a source, and I just finished a paper on that. In fact, I just sent it out earlier this week to colleagues at both Fermilab and then a gentleman working. He's in England and he's associated with CERN, and it's going to be. I'm trying to show that this does work. I studied all of the various scattering events, just like I did for the fusion device, and that may end up getting DOE interest because when you've got something that's desperately needed and there really aren't that many alternatives, then you've got a much better shot. Whereas fusion, you're dealing with a community that is already well entrenched and believes in what they're doing. It's a lot harder to get in the door because there's a belief that the solution's just around the corner. Where I don't believe in most of the muon collider community, when it's a sober look, there's some. It's a very difficult project, and we're pushing technologies in many different areas to try to make it work. And if you can add a new one to the mix, it may be welcomed. I mean, clearly it needs review, as all my work always does, but I'm optimistic that that will be the first step to start proving this technology, and then we can get things rolling.
Well, so you're in the scientific community, working in the scientific community. How would you say, how do you feel that, what has the reception been of your quantum luminiferous ether theory in the scientific community? And how do you think that that can move forward in a positive direction for you?
That one's going to be tough. And the reason it's going to be tough is I don't know if you saw the recent, it was great. Did you see the Piers Morgan debate with Eric Weinstein and Sean Carroll?
No.
Oh, yeah, take down a note on that one.
It came up on my radar screen, but I don't like conflict, and
Oh,
I was a little afraid it was going to be one of those combative conversations. But if
yes,
you
it
recommend it, I'll go take
was.
a look at it.
Well, I mean, it was, but you asked the question, and the thing is that Eric has been working extremely hard to try to get his model. Uh, I'm not sure what the right word would be. I guess validated
Mhm.
by the peers, and when I watched it, I just realized he's a cousin, of what they're doing. I'm another species. It's because he's a mathematician like everyone. He's got that's in the physics community now. In my view, what happened, I guess we got a couple minutes maybe. Einstein took the first step to take physics away from an underlying physical modeling for what makes up our world. He was very brilliant, and it answered certain questions.
Now, by
And then
when you say that, you mean kind of removing the idea of objective reality and replacing it with,
no, he was 100% into objective reality.
okay,
What he did, though, was he changed what was the prevailing notion of space and time,
okay.
which was a very big and bold step. And I believe
So
he
no
was
longer
not
absolute space and absolute time, but rather the time-space continuum model.
correct.
Okay.
And one can become another depending on your relative motion. And so it's kind of a bit of a strange concept. And then Minkowski came in and added a contribution to show that there was a four-dimensional. I mean, Einstein had this too, but it's called a Minkowski space because if you multiply time by the square root of -1 and the speed of light, you get a coordinate system where everything is measured in length units. And so you have this four-dimensional continuous space-time. And then later he added gravity by saying that it is on a curved manifold. So that was the first step away because when you look out the window, like I'm doing now, I see one dimension. In fact, I generally would say that we have three spatial dimensions. We have depth, height, and width. And I would say that time is a completely separate entity. This is now heresy. So,
Mhm.
so that's a problem, which and it's a problem that is very difficult to overcome because the present view that there's a space-time continuum is viewed as one of the greatest achievements that mankind has made intellectually in the last over 100 years now. And so there's that. And then the next big step away, then that because then what came was the quantum revolution came next. And we had the Schrodinger equation, and Schrodinger and Einstein kind of looked at things very similarly from a perspective of the philosophy of quantum mechanics. And that wasn't really too far of a step away further, but that was where you got into the debate about whether things are points or continuous and all of that. And I continually bang away that the quantum is a wave packet and it's not a particle ever. It's never a point-like entity. Relativity is a point-like theory. So there's a big hurdle there. See, and on the Weinstein-Carroll debate, they're pretty much in step on relativity still being sound. But then the next step along the path was when Dirac came, because the Dirac equation is really where things kind of got a little bit off the. I would say it was the step that really took us off of a physical model for sure, because he linearized the equation e squared equals p squared c squared plus m squared c to the fourth by throwing in some 4x4 matrices and a four-dimensional spinner. But the entities within those matrices and within that spinner don't specifically have any physical meaning, but the four-dimensional spinner did leave four solutions that were somewhat loosely correlated to an electron spin up, electron spin down, positron spin up, and positron spin down. That was viewed as a tremendous success. But the problem was you don't have a physical picture anymore. So what I'm struggling to do is to go back to the time before almost all of that, at least from a foundational standpoint, and go back to a physical model. And that's it just goes way back. I certainly accept, not only do I accept, but I have shown how that model leads to a quantum mechanical theory. So everything's there. I'm not saying that we should go back to Lorentz and just, that's everything. No, not at all. But I'm saying that the basic fundamentals, the primitives that we use, space, time, entities of themselves, things in themselves, not this mathematical overview and think that that's actually what things are. When you read quotes from Dirac, you'll see that it says God was a mathematician. And in my view, no. I mean, certainly there's math there, but I look at a physical basis for physics. And what has happened is the theoretical physics departments really, in my view, are largely mathematics departments. And there aren't too many physical models around. So when you ask about where things are, that's where it is, and it's going to be an uphill climb. But I think it might land well with the engineering minded, and so that's where things are today.
Well, I have thoughts, but this has been a long talk, so maybe we need to stop here. At some point, maybe it would be fun for me to talk to you about Wolfram's theory, because Wolfram's theory also is looking at space and time very differently than the Einstein's relativity. Although apparently, using his theory, you can still come up with Einstein's equations of relativity. So it does fall out of the theory, but he sees space as being made up of particles and
Yes.
time as being the updater of events.
Yes. And I don't. I think space is the stage upon which events play out, and time is the order that they occur. Space is measured by meter sticks, time is measured by clocks. And that's my view of it, which is different because I have looked at Wolfram's some, and it's a pretty significant difference at that point. Now, his space may not be as different from my ether, but I
Mhm.
wouldn't confuse the ether as space because the ether is something which occupies space. We may well live in a giant ethereal ball in space. It may have an edge. There may be other balls further out in space. We wouldn't be able to see them because light travels within the ether that we live in. So that's a pretty different view, I think, than what I've seen that he is promoting. But there is the overlap that I and he both think there's a substance there that others
Mhm.
are missing.
Yeah, yeah. And you're both on an uphill climb. Although
Yes.
he has a lot more visibility, so he's able to um and a lot more finances because of all the company he started. So he has the capacity to hire people and get visibility and all of that. But
Yeah, I'm
I,
working on it. And I want to thank you for your contribution by having me on your show here today.
well, I have a very
Thank you.
small audience, but hopefully some of the people in the audience are people who can carry this elsewhere. So
All right.
it's been a delight talking to you today. Just so much fun. I've learned a lot. You're an excellent teacher. You take these very complicated ideas and break them down in a way that I can understand, even though I'm a total novice at all this stuff. So I really appreciate that. And I appreciate your patience with my questions. So all the best. And maybe we can get together again in another year.
Sounds great. Thanks for the time today.
Okay. Have a great weekend.
Bye.